China just revealed a jet engine that sounds almost impossible, one that changes shape mid-flight to stay efficient from takeoff all the way to Mach 4. Built by the Institute of Engineering Thermophysics, this adaptive cycle engine could deliver nearly 50% more thrust while burning a third less fuel. If true, it's not just a new engine, it's a revolution in how fast, efficient, and intelligent aircraft could become. The new engine developed by China's Institute of Engineering Thermophysics, IET, is claimed to deliver outstanding performance by employing an advanced adaptive cycle architecture that dynamically switches between flight regimes. Unlike traditional engines optimized either for high thrust, turbojets, or for efficiency, turbofans, this design reportedly spans from takeoff through subsonic cruise all the way to a Mach 4 envelope. According to reported figures, the engine delivers 27 to 47% more thrust than similar class engines, while reducing fuel consumption by approximately a third. Critically, this engine features a three-stream bypass architecture, in contrast to the U.S. adaptive engines such as the GE XA100 and Pratt and Whitney XA101, which use dual bypass streams. The third stream provides a cooled air path that enables better thermal management, lower infrared signature, and higher efficiency. Moreover, the Chinese prototype integrates bypass combustion capability, meaning fuel can be burned in the bypass airflow for extra thrust at high speeds, bridging toward combined cycle propulsion. This helps overcome the thrust trap problem in supersonic flight, where conventional turbofans lose performance at high Mach numbers. In effect, the system promises to deliver high specific thrust during rapid acceleration or high-speed dash, while switching to high fuel efficiency mode during loiter or subsonic cruise. The variable geometry mechanisms and mixing of streams allow the engine to modulate bypass ratio, pressure ratios, and core flow dynamically. While the full production integration remains to be seen, the engineering principles are consistent with ongoing research into three-stream adaptive cycle engines. What makes this engine more than an academic exercise is how it alters the performance equation in aviation. If the claim of up to 47% increased thrust and roughly 30% lower fuel burn holds in operational conditions, it opens a wide range of possibilities. For future aircraft, this means longer range, higher speed, and reduced logistic burden, especially valuable for extended missions. A higher thrust engine enables steeper climb, higher cruise speed, and heavier payload. At the same time, better fuel economy gives more time aloft and greater flexibility in operations. For stealth or low-signature platforms, the cooled third stream offers lower exhaust temperature and reduced infrared signature, an increasingly critical dimension in sensor-rich environments. The ability to burn fuel in the bypass stream also smooths transitions between subsonic and supersonic flight, helping sustain higher speeds for longer without excessive fuel cost. Comparisons to Western adaptive engine efforts are inevitable. The Chinese variant claims both higher thrust and broader speed range up to Mach 4, suggesting a direct leap rather than incremental improvement. The United States XA100 and XA101 adaptive engines are designed mainly for aircraft like the F-35, targeting Mach 2 plus performance, while the Chinese approach seems to aim for much higher regimes, possibly bridging the gap between turbine and ramjet technologies. On the civilian side, the technology could enable sustainable supersonic transport. Imagine an airliner that cruises efficiently at subsonic speeds but can push to higher speeds when needed, all with a single adaptive engine rather than separate propulsion systems. The implications extend to global travel, aerospace innovation, and competitiveness in advanced propulsion systems. In broader strategic terms, propulsion breakthroughs affect not only individual aircraft but also national aerospace independence, manufacturing capabilities, and future design freedom. Despite the impressive numbers, caution is necessary before calling this a fully operational leap. The available data originates from early technical announcements and laboratory testing rather than verified flight trials. The Mach 4 figure may reflect simulated airflow or wind tunnel results, not sustained powered flight. Turning a lab-tested prototype into a reliable operational engine remains a massive challenge that could take years of additional development. Operating at Mach 4 with a turbine-based engine presents extreme material and thermal constraints. At those speeds, the temperature at the engine inlet can exceed 1,000 degrees Celsius, which pushes the limits of even advanced superalloys and ceramic coatings. Variable geometry components must move smoothly under immense stress, and cooling systems must handle the heat without compromising structural integrity. The control systems for an adaptive cycle engine are also far more complex than for conventional turbofans. Managing three airflow paths, modulating bypass ratios, and switching between operating modes requires sophisticated sensors and AI-driven control algorithms. Even slight timing errors could lead to pressure surges, flameouts, or efficiency losses. That is why long-duration testing, high Mach flight validation, and integration into actual airframes are essential next steps before any real deployment. It's also important to note that many ground test successes worldwide never make it into full production due to cost, reliability, or material limits. But even if the current prototype is still years away from operational status, it signals a powerful trend. The global push toward engines that combine efficiency, power, and flexibility in one package. China's new engine claim may mark a major leap in thrust, efficiency, and flexibility, but until flight tested on an operational platform, it remains a breakthrough in progress. If the promise holds up, we could be witnessing a turning point in how fast and how far future aircraft fly. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries, and don't forget to leave a comment below. Thank you for watching, and see you next time.